All right, so a pro football team measures players' potential for positions based on two main traits, speed and strength. All right, speed is measured by the time required to run the distance of 40 yards, with smaller times indicating more desirable or faster speeds. From previous speed data for all players in the position, the time to run 40 yards have a mean of 4.55 seconds and a standard deviation of 0.17 seconds, with a minimum time of 4.30, as shown in the table below. So here is all that information summarized in the table below. Based on the relationship between the mean, standard deviation, and minimum time, is it reasonable to believe that the distribution of 40-yard running times is approximately normal? Explain. All right, well, what happens if it is normal? So if it is normal, then we would have a mean of 4.55. 4.30 would be somewhere down here, right? There would still be area here, I think, right? And we can actually calculate that area. Normal CDF. Lower bound would be something small like 0. Upper bound would be the 4.30. Mean would be the 455. Standard deviation would be the 0.17 that they gave you. And since my calculator will not open, which is a new thing, it opened earlier when I was using it yesterday. Computer has just been all sorts of weird in the last couple of days. 0.17. And I get this equals 0.07. All right, so if this was normal, so if this was normally distributed, we would expect 7% of the times to be below 4.30 seconds. All right, so now did I answer the question based on the relationship? Is it reasonable to believe that the 40-yard is approximately normal? All right, so I haven't answered their question yet. So this must not be normal. Because 4.30 is the minimum. All right, let's see what they said. All right, so one thing they did is they looked at z-scores. So this is one way to do it, is to look at z-scores. So if it was normal, we should be able to go down z-scores to -3 and up to +3, but -1.47 is the lowest. All right, so that would be a thing. So we'd say no, not normal. And that's our reasoning is the z-scores should be able to go down farther than -1.47. The other way to do this is the way I did. So it's not normal, and I did the normal CDF. This again should be labeled lower, upper, mean, and standard deviation. Otherwise, you don't get full credit. You get a P. We get that answer. So we would be missing 7% of the distribution if it was normal. All right, so there's multiple ways to go about answering a lot of these questions. So this is a good one that shows that there is multiple ways. All right. Next up, all right, so now we're measuring strength, where greater numbers are better. We've got a mean of 320, mean of 320, standard deviation of 30. Calculate and interpret a z-score for a player in this position who can lift a weight of 368 pounds. That's 86 pounds. So this is a two-part question. Calculate and interpret. I have no doubt that all of you can calculate a z-score. X minus the mean divided by the standard deviation. In fact, I'm doing this in regular statistics right now. So this would be 386 minus 320 divided by 30. And let's see, on my calculator, 386 minus 320. I could probably do that in my head and get 66 divided by 30. We get 2.2. All right, now it says to interpret. All right, so that's probably where people lose points if they lose points here. So 2.2 means that this weight, so 386 pounds, is 2.2 standard deviations above, it's positive, so above the mean, then the mean of the 320. All right, so that's what this z-squared means. It's the number of standard deviations something is above or below the mean. All right, so this would be pretty high. All right, so there's our z-squared 2.2. The amount of weight the player can lift is 2.2 standard deviations above the mean. All right, so z equals 2.2 with the formula and calculation. So if you did not write out this formula, you did not get full credit for the first point here. 2.2 standard deviations above the mean is what they were looking for there. We didn't really need even any context on that one, strangely enough. Usually we do want context, so try and include context if you can. All right. Next one. The characteristics of speed and strength are considered to be of equal importance when the team selecting a player for this position. Based on the information about the means and standard deviation of the speed and strength data for all players and the measurement listed in the table below for players A and B, which player should the team select if they can only select one of the two players? Justify your answer. All right, so you guys did have this like exact question on a test. It was just with basketball, it was jump height and speed were the two things we were looking at there. This is the question I used to make that question. All right, so we've got our 40 mean and standard deviation, and we've got our weight lift mean and standard deviation, and we've got the numbers for each player. So let's just go ahead and calculate z-scores for each player. So for player A, all right, so we've got the runtime, z sub A, I guess I could call that, is their number, 4.38 minus 4.55, the mean, right? This mean right there, divided by this standard deviation, 0.17. And for weight lift, d sub A would be, let's see, they lifted 370, so 370 minus 320 over 30. All right, and remember, small is good for runtime, below the mean is good, above for weight is good. So lifting more is good, running faster is good. All right, let's do the same thing for player B here. So we've got run. So z sub B here would be, let's see, we've got their runtime was 4.53 minus the mean, which is 4.55 over 0.17. That looks like it's going to be pretty close to 0. All right, and weight for player B. So we've got 375. So they can lift more minus the 320 divided by the 30. All right, and now we need to calculate each of these. So let's pull out my calculator. 4.38 minus 4.55 divided by 0.17 gives me -1. So that's 1 standard deviation below the mean. So 1 standard deviation better than average. 370 minus 320 divided by 30 gives me 1.667, I guess we'll say. So this 1.67 standard deviations better than the mean. Again, lifting more is better. For the other one, we've got 4.53 minus 4.55 divided by 0.17, which is -0.12. It's 1176 and something, but negative. So that's very close to it. It's slightly better than average, but very close to the mean. The next one, 375 minus 320 divided by 30 gives us 1.83. All right, so now based on that, who are we taking? Player A or player B? What do you think? Looking for some answer in the chat here. A is better or B is better? Really? So all 3 people that responded all said B, huh? I'm gonna go with Anthony here. I'm also gonna go with player A. All right, so this beats this by a lot. All right, that's almost 1 full standard deviation better. This and this are pretty close. All right, 1.67, 1.83. This guy's a tiny bit better. All right, so I would say choose player A. All right, so for the weight lift, they both have similar z-scores. But for the runtime, player A is much better. So that's why I would choose player A. All right, because negative is better for the run times. Positive is better. Like the higher positive is better for the weights. Lower negative is better for the runs. All right. Another way to think about it is, well, these guys, they only lift 5-pound differences. When we're looking at 300 pounds with a 30-pound standard deviation, that's not a huge difference. Like 5-pound difference, 5 over 30, that's what, 0.16? That's a very small difference. But if we look at these two differences, 4.53 minus 4.38, and divide that by 0.17, that's a difference of almost 1 whole standard deviation. All right, it's a difference of 0.88 or about 0.9. All right, so these two are almost the same, or they have a difference of plus or minus 0.167. These two have a difference of 0.88. All right, so A is better. Like if we look at these two differences and subtract them, we still end up with A being overall better. All right, if we wanted, we could take absolute values of these and kind of add them up and just give everybody a score based on that. This guy would be 2.67 better than average. This guy would be 2 better than average. All right, if we took absolute values and added them up. About 2, a little under 2. All right, so did I calculate one of those wrong? Or do I have the answer wrong? No, I have the answer wrong. So this is 5.3, not 5.5. So you know what I did? No, it is 5.5. Did I just calculate something wrong? I don't know what I did, but something is slightly off here, but the numbers still work out to almost exactly the same thing. Like this was the only one that was different. Maybe I just typed it in wrong there for that one. Let me try again. 4.35 minus 4.55 divided by 0.17. Yeah, that is 1.18. Oh, it's 3.5 and this says 3.8. Okay, maybe I changed it when I was. So I sometimes edit these and change them to have different numbers. So if it is 3.8, that's fine. This just becomes 1 exactly, but it still works out to the same answer. All right. So while the lift scores, z-scores are about the same, about above the mean, the running z-scores are more than 1 standard deviation apart in favor of player A. Choose player A. So we need to select player A in your answer. Comparisons of lift using standard deviations as the scale. All right, so in other words, we're saying that these two are pretty close to each other. Comparisons of run using standard deviation of the scale. These two, A is much better. All right, and then that's our justification for choosing part A. All right, so kind of a complicated question there, but none of the math was super difficult, just complicated. All right, and there's our scoring there, which is our typical normal scoring breakdown. All right, our second free response question. So the table below shows the political party registration by gender of all 500 registered voters in Jefferson Township. So we've got male, female, party X, party Y, party Z totals here. So given that a randomly selected voter is male, what is the probability that he is registered for party Z? So we're only looking at males. So that means we're only looking at this thing right, that circled row right there. And we want, what is the probability that they are party Z? So here's the party Z ones. Here's the total number of males. So we'd say 48 out of 200. That's all you have to write. Like if you wanted to get more complicated and we want to say, given that they're male, party Z, so we want the probability of Z given that they're male like that, equals probability of Z and male over the probability of male, and then say that this is 48 out of 500. And this is 200 out of 500 equals 48 out of 200. You could do that if you wanted to. That's a lot harder way to go about doing it. For me, it's easier for me to just look at this and says, well, okay, given that we're male means we're only looking at these 200 people here in this row. And then out of those, what's the probability that they are party Z? Well, 48 of them are in party Z, so 48 out of 200. If you want to say that's, is that 0.24? That's fine too, but you do need to show this work here. They want to see the work. All right, so there's our answer. Has this answer shows that. Calculates the, oh, okay, so that's the reverse. All right, so again, really, if you just had this, that is full credit because that is a probability. If you worked out the answer, more power to you. But if you just had this, that's not full credit because they want to see work. All right, if you did it backwards, like the probability of male out of party Z, so like if you did like this, instead it was 48 out of the 168 here, you still get a P for that. So even if you do the wrong thing here, if you were still doing some sort of conditional probability with male and party Z, they're still giving you a P on this problem. So they're pretty lax here. Part B, among the registered voters of Jefferson Township, are the events is a male and is registered for party Z independent? Justify your answer based on probabilities. So we already looked at the probability that they were in party Z given that they were male. Instead, it was 48 out of 200, which is 0.24. This is our answer from A. But we can look at it the other way around now. What's the probability that they are male given that they are in party Z? So that would be one way to do it. And that would be, so this right here, out of party Z would be out of 168. And those that are male out of that would be 48, which is not that right answer. 48 divided by 168 is 0.2857 and so on. All right, so these are not the same. Different probabilities. Therefore, not independent. All right, there are other probabilities we could also look at. So we could also compare it to just what's the probability that somebody's in party Z. And that would be 168 out of 500. And 168 out of 500 is 0.336. And since those two are different, you could also say not independent. All right, so there's lots of different things we could look at here. Well, you could do it the other way around too. Like you could do the probability of male versus the probability of male given that they're in Z. That would also work. So the probability of male is going to be different than this number. So there's lots of different ways you could do this. All right, I tried to write some of them here. So this is one of the ways that you could do it. More independent implies that this, yeah, I did it the or here. This is the shorter way. So the probability of Z given that their male is 0.24 is not equal to the probability that they are in party Z, which is the 0.336. There are lots of things we could compare. So as long as you said not independent, you calculated two probabilities. One of them is probably that probability and compared them saying that they were not equal and said not independent because of that, you're good. So independence also tells us that this is true. So probability of male times probability of party Z would equal the probability of male and party Z. So the probability of male was 200 out of the 500. The probability of party Z was 168 out of 500. And if we multiply those two together, if it's independent, that should equal the same thing as the probability of male and Z. So it's just other rules that come with independence. There's lots of them. And since that didn't hold, that's not true, not independent. All right, the last part here. All right, so the table below shows the political party registration by gender of all 500 residents of Jefferson Township, blah, blah, blah. One way to display the data in the table is to use a segmented bar graph. The following segmented bar graph constructed from the data in the table above shows party registration distribution for males and females in Jefferson Township. So this is for Jefferson here filled in. That's what it would look like for a segmented bar graph. In Adams Township, the proportion of all registered voters for parties X, Y, and Z are the same as Jefferson. Okay, cool. So that means these totals, when we look at those proportionally, they are the same. And the party registration is independent of gender. So that means for male and for female, the party breakdown, the proportion should be the same. Complete the graph below to show the distribution of party registration by gender in Adamstown. All right, so I didn't have room to put it on here, so I'm just going to put it there. So for Adams, since it's the same proportion, the probability that someone is in X would be 88 out of 500. The probability that someone is in party Y would be the 244 out of 500. And the probability that someone is in party Z would be 168 out of 500. All right, regardless of gender. So this will be the same for each gender. All right, so if we do those divisions, which I'm frantically doing right now on my calculator, we get 0.176, 0.488, and 0.336. So that means for both of them, we should be about at 17.6. And I'm just going to go ahead and label this 17.6%. And this would be there's that, and that was party X. So I'm labeling it. All right, I'm going to then switch colors. I have the ability to do that. You guys probably don't. Party Z is 33.6. So if I come from the other end and go to 33.6, it's going to be probably about there. All right, so this section here, coming from the other end, would be Z. And again, it'd be the same for both males and females, Z. And then what's left in the middle, this part here, and this part here, again, exactly the same for both, would be party Y, which should be 48.8%. So if I subtract from there to there, that should be about 48.8. Right. If you want to label this, you could do 100 minus the 33.6, 100 minus 33.6, and this would be 66.4. All right, so you could label it there if you wanted to, but as long as it's going to look approximately right, the sections are broken down that they are the same for each one, like those match, you've labeled each section, you should be good. All right, so there's what it looks like down there with shading and stuff. And there's those proportions that we calculated. All right, so same distribution for each gender, correct proportions, labeled X, Y, and Z on the graph. So I labeled it down here at the bottom, but really just writing on the graph X, Y, Z. That's plenty. All right. So that's how we do problem 2. And again, same breakdown here. All right, so that took 20 some minutes or so. Let's see, how are we doing here on the multiple choice? So now we didn't get a ton of people that did the multiple choice, sadly. Looks like online dating here was about the worst. Hopefully you guys were ones that did do the multiple choice. Oh boy, what did they do? All right, so a random sample of 240 adults over age 40 found that 144 would use an online dating service. Another random sample of 234 adults age 40 and under, so that would be me. I just barely make that one, age 40. 131 would use an online dating service. Assuming all conditions are met, which of the following is the standard error for a 90% confidence? All right, so the 90% doesn't really mean anything. So standard error when we're working with two sets, so it'd be P1 hat, 1 minus P1 hat over that sample size, plus P2 hat, 1 minus P2 hat over N2, like that. All right, so let's see. This, we could say this is N1 equals 240. So then P1 hat would be 144 out of 240. And then N2 would be this 234. And then P2 hat would be the 131 out of 234. All right, and I don't know how much you can actually read that, but there's P1 hat right there. And there it is again, 1 minus it. And there's N1 down there. And then we've got plus, yep, always plus. Even if we were to subtract and to find the difference, we're still going to use plus. All right, and then we've got the 234 down there, yep. We've got P2 hat right there and right there. And 2 didn't really show up well here, but there we go. All right, so that's how we do our standard error here. All right, now looks like 11 people went with that. That would be the margin of error, not the standard error. So the standard error is just like their other name for the standard deviation using these samples here. So this is the standard deviation is what we really just want. So when they say standard error, they mean like just what are we using as the standard deviation? So it's just that part. Like it looks like you've got this part correct though. So the 11 people that went with that, you've got that correct. And this is the correct Z star. I believe 1.645 is what 90% works out to. So 1.65 would be fine. But that is not how we do standard error for this. And one of these would be pooled data. I think this one would be the pooled, actually, this one would be the pooled standard error, and this one would be the pooled margin of error. But since we're doing a confidence interval, we don't pool data at all. If we were doing a hypothesis test, then we could pool the data. And that would be also correct. All right, so let's go back here. Let's clear this out and let's see what else did we really struggle on. So that was this one. This one looks like another toughie. All right, so which of the following indicates that the use of 2 sample Z interval for a difference in population proportions is appropriate? 2 populations of interest exist. Yeah, that could. The variable of interest is categorical, meaning, yeah, we would look at the number that said yes versus the number that said no. Yeah, that would work. The intent is to estimate the difference in sample proportions. All right, so the key thing here, and I see we split evenly between those two basically, is the word sample. If it said population right here, then we would say 1, 2, and 3. But this says sample proportions. We don't want to estimate the difference in sample proportions. We want to estimate the difference in population proportions. We can find the difference in sample proportions. It would just be P1 hat minus P2 hat. That's what that would literally equal. All right, so you got to look for these little words here, sample and population. They make a big difference. All right, inference, we're always inferring about populations. So it says the intent is to estimate that difference. Not for a sample, for a population. All right, so one word got us there, huh? Shucks. All right, let's clear this out. There was another one here that had 10. So that was this one, diagnostic tools. Looking at error types here, huh? So researchers are testing a new diagnostic tool designed to identify a certain condition. The null hypothesis of the significance test is that the diagnostic tool is not effective in detecting the condition. For the researchers, the more consequential error would be the diagnostic tool is not effective, but the significant test indicates that it is effective. All right, so that would be type 1 error, because then the null hypothesis would be true, and we're going with the alternative hypothesis. Which of the following should the researchers do to avoid the consequential error? Increase the significance level to increase the probability of a type 1 error. So we've got, I need to write this out. It is effective, so oh, sorry, is not effective. Sorry, there is a not there. I just missed it. So our alternative would be is effective. All right, so if we increase the significance level, we would increase the probability of a type 1 error. We want to decrease the probability of a type 1 error. All right, because it says the more consequential error would be the diagnostic tool is not effective, but the significance test indicates that it is effective. So this right here that it's describing, that is a type 1 error. So we want that to decrease. So if we increase the significance level, that would increase the probability of a type 1 error. That's the exactly opposite of what we want. increase the significance level to decrease. Well, the significance level is the probability. So those two go hand in hand. All right. So we do want to do that, but this won't do that. Decrease the significance level to increase. Nope, they both go the same way. So like, remember, alpha equals the probability of a type 1 error. I mean, type 2 error, it gets a little more complicated and stuff, but here alpha is exactly equal, and alpha is our significance level. So when we're talking about significance level, that is alpha. All right, decrease the significance level, yes. To increase, no, we don't want to increase. Decrease the significance level to decrease the probability. Yeah, that's what we want to do. Decrease the significance level to decrease the standard error. Oh, how did standard error make it into this? No, I don't want anything to do with standard error. They just needed another option, apparently. All right, that one was tricky. I'll give you that one, especially the wordiness of it. So that was 8. And let's see, there was another couple here that had 10. Clear that out. If all other factors are held constant, which of the following results in a decrease in the probability of a type 2 error? So type 2 error is a little different. Type 2 error is, let's see, the probability of a type 2 error plus, what was it, beta, or the power of the test equaled 1. That was something we had. Let's see, what else did they do down here? So the true parameter is closer to the value of the null hypothesis. Boy. So if we had the, let's see, here's one curve, and then the true parameter is the second curve. So this is the null, so like P0, and this is the true P. So if they are closer together, that actually gives you a higher probability of making a type 2 error. Right? Because they're closer together, like this curve will be close to this guy. But if they're farther apart, that actually gives us a smaller probability. So we actually want the opposite. We want them to be farther apart. Sample sizes decrease. Sample size decrease. So remember, we've got the square root of n on the bottom. All right. So if we decrease the sample size, that means that our standard error and our margin of error will both decrease. All right. Actually, take that back. Will both increase. Sorry, because we're dividing by a smaller number here, so the whole thing is going to get bigger. Right? We don't want those to get bigger. That would really mean like taking this curve and making it this curve instead, which would mean there'd be more area out here. So we don't want to do that. We could actually do the other way and say increase. That would work. Significance level is decreased. The significance level doesn't have anything to do with this. All right, decreasing it actually would be the opposite from what we'd want to do. We'd want to actually increase it, but that's minor details. Standard error is decreased. Okay, so if these guys get smaller, that means our curve looks more like this for each one. And that means there's less overlap between the curves and less chance of making that type 2 error. So yeah, that one is correct. Probability of type 2 error cannot be decreased, only increased. No, that's not true. No, bad, just bad. All right, so this one is a very tricky, weird question. But if you think about what's happening with the two separate curves, one for the null hypothesis, one for the true p-value, and think about what would change those curves and what would make the p-values bigger and smaller, then you could see what's happening there. There's one more here. And it's more of the same stuff. All right, so let's go into the next section here. See if we did any better here. Actually did a lot better here. Okay. Nope, except we got tired towards the end. Genetic trait. Let's see. Medical researchers are studying a genetic trait found in two populations of people, W and X. So those are our two populations. For an independent random sample of people taken from each population, the difference between the sample proportion of people who carried the trait, W minus X, was 0.22. So 22% difference. That seems pretty substantial to me. Under the assumption that all conditions for inference were met, a hypothesis test was conducted with the following hypothesis. All right, so we've got that they're equal or that P sub W is greater. W minus P was 0.22. So yeah, it said that would be the same thing as P sub W minus P sub X is greater than 0. And we've got that it actually equals 0.22. So that's a good sign. The p-value is that, oh, that's a small p-value. Yeah. Which of the following is the correct interpretation of the p-value? All right. So here's the tricky thing. They do like to ask these interpret the p-value questions. And the way this works, it means if the null hypothesis is true, the p-value is the probability of getting this difference or more extreme, like or farther away. All right, so let's see. If the proportion of all people who carry the trait is the same or are the same for both populations, so that's this being true. So that's what this is saying from here to here. So that's what we want to start with. Then the probability of observing a sample difference of at least 0.22. So that much or farther away is 0.03. That's what we want. So if we read the other ones, why are the other ones wrong? So the probability of selecting a person from population W who carries the trait is, no, it doesn't have anything to do with that. If the proportion of all people who carry the trait are the same for both populations, okay, that's a good start. The probability of observing a sample difference of 0.2 is, so it's not exactly that. So remember, when we're looking at a normal curve, when we're doing this test, like this middle here would be like PW minus PX. And then we'd be getting, here's our P hat W minus P hat X would be here. And then the P value is from there on. So that's why I try to write it differently all year with putting the P capital P dash value, because we have so many different P's involved here. But it's not exactly that. It's that or farther away. It's this answer that we get from our sample or more extreme. So if we do a two-tailed test, then we have to add in the other side too. And the P value takes that into account. All right, so, all right, yeah, so the other one, they're saying the difference is that, we don't want to say that. So yeah, it's B is our guy right here. So that's just a matter of remembering the definition of a p-value. And we did go over it in the very beginning, but I didn't press that enough. I should have gone over that more. Should have put that on some tests, but I didn't. All right, so let's see, what else do we have in this section here? We'll call it soon, guys. I know some of you are getting tired. So let's see, driving to school. And we'll do the one more that had 10 wrong after this, and then we'll call it quits. All right, so let's see. Independent random samples of students were taken from 2 high schools, R and S, and the proportion of students who drive to school in each sample was recorded. The difference between the 2 sample proportions, R minus S, was 0.07. This is asking us to do the same thing. P-value is this. Which of the following is the correct interpretation of the p-value? So it's the same question, really. So if the null hypothesis is true, so if they are equal to each other, hypothesis test was conducted where the alternative hypothesis is that the proportion for R was greater than P. So this is the probability that we would get a sample as extreme as we got, the difference of 0.07, or farther away. All right, so the probability of all students drive to school, if the proportion of all students who drive to school are the same for both high schools, the probability of observing a sample difference of at least that we got, that difference, is this probability. So that's how we interpret p-values. There's the other one. There's the other one. All right, so this isn't asking us to do the same thing, is it? No, it's not. All right. So researchers are studying starfish, collected 2 independent samples, random samples of 40 starfish. 1 sample came from the ocean in the north, the other sample came from the ocean in the south. Of the 40 starfish in the north, 6 were found to be over 8 inches in length. Of the 40 in the south, 11 were found to be over 8 inches in length. Which of the following test statistics for the appropriate test to investigate whether there is a difference in proportion over 8 inches in length and the 2 ocean areas north minus south? All right, so what they're doing here, and it looks like they are pooling data as well. So I can understand getting this one wrong, but 7 people got it. So what they are doing here is they're doing, let's see, p hat. I'm going to call it p hat, but it's actually p Is it north minus south? Or are we doing south minus north? One sample, that was 11. Is just a difference in the, all right. So P north minus P south hat minus 0. Like the difference is 0 is what we're assuming. We just want to see, is there a difference? Divided by the standard error is what we really do here. All right, so the standard error here would be, well, there's two ways to do it. You can do it pooled or not pooled. They've started doing more things pooled. So if they're doing things pooled, what ends up happening, it's kind of weird, is we have 6 out of the 40 and we have 11 out of the 40. So let's see, P south. No, this is north. P north hat would be 6 out of 40 and P south hat would be 11 out of 40. So what they're doing is they're making a combined P, like P hat combined would be 6 plus 11 out of 40 plus 40. And that would be what, 17 out of 80? And let's see, 17 out of 80 is 0.2125. Right? So then what they do, the formula basically is P hat pooled 1 minus P hat pooled of the sum of 1 over each of the sample sizes. All right, this is a formula that is on the formula sheet, by the way. All right, so we have the difference on the top, and this could go in either order. It doesn't really make a difference which order they go in. All right, because it says not equal to, so it could be like just one bigger, it could be one smaller, it doesn't make a difference. So that can go in either order. But this is going to be 0.2125. 1 minus that, I believe, is the 0.7875. And then we've got 1 over 40 for the one sample, 1 over 40 for the other sample. There's our standard error, our pooled standard error. And on top, we've just have the difference between the two proportions. So we could go either way. Looks like they're doing the 0.15 because this would be 0.15 and this would be 0.275. So they're doing the 0.15 minus the 0.275. But really, either way, you can put those and that's fine because we're just looking, is there a significant difference? So we want to see how many standard deviations away from each other are there. Yeah, that's okay if you missed that one. I don't blame you there. All right, so we will stop recording here.